So we talked yesterday, we started talking about linear equations, especially or really only in one variable. We usually call that variable x. And we talked about how you can solve them. You may have to use several mathematical properties. You may have to add or subtract a number from both sides, multiply or divide a number on both sides of the equation. You may even have to use distribution and combining of like terms before you can actually jump in and start balancing the equation and everything. What we're going to talk about now are things called contradictions and identities. Contradictions and identities. Going to be interesting stuff. What we're going to find is that a contradiction is when you arrive at an equation that for whatever reason cannot ever possibly be true. Remember, the whole point of solving equations is all about finding value or a values of the variable or variables if you have more than one, which we don't yet. It's all about finding values of the variables that make the equation a true statement, that do not make it a liar. But you're going to find in practice when you work some of these, you're going to run into equations where no matter what value of x you plug in, you're never going to be able to produce a true statement. What that means is that x is actually going to end up being eradicated from the equation. And that's called a contradiction. But you can also run into identities, which are situations where x eventually can be eradicated from the equation, and then you're left with a statement that is patently false, that could not possibly be true. And since x is gone, x can't fix the situation. So there's going to be no solution whatsoever to that equation. Let's take a gander at that. Let's say we wanted to solve, and we'll start off trying to solve it with our usual methods. We won't pull any fancy trickery. Let's start off trying to solve gussy that up a little bit. That's a nice minus sign. There we go. So 3x plus 7 minus 5x on the left-hand side. 2 times, in parentheses, 4 minus x. So this is about as complicated a one variable linear equation as we're liable to solve. Well, let's see here. What should we do first? What do you guys think? Yeah. We can distribute the 2. And then, so we can do that first. What else could we do? Is there anything else we could do maybe all at once? Yeah, very good. Anytime you can combine like terms, 9 times out of 10, 99 times out of 100 even, you're probably going to have to. It's probably going to help you to do so. And so what we'll do on the left, we will combine like terms on the left-hand side of the equation. So let's see what kind of wonders that yields us. What will the left-hand side of the equation become as a result? Very good. Negative 2x plus 7. What will the right-hand side become after we distribute? Very good. Perfect. 2 times 4 is 8. There was subtraction there. 2 times x is 2x, so it's 8 minus 2x. All right, what should we do next? Yeah, we would, in any normal equation, not knowing that this one's going to end up being special, you would try to get all the x's A in Texas, or B, if you can't help that, get them on the same side of the equation and combine like terms. In this case, that's what we're going to do. I'm going to move this 2x over here by adding it to both sides. Wait a minute. We didn't do anything wrong. We're still completely right. What's going to end up happening? No, x, exactly. X is gone. X is no longer going to give it to you. It's going to be completely eradicated from the equation. Negative 2x plus 2x, well, that's 0. Heck, I'm not even going to write it because you don't need to. All that I have left is 7. We know we were moving this 2x over, so it's gone on the right-hand side, and I'm left with 8. Now, wait a minute. Whoa, Nelly. Wait just a New York minute. Now, I may not be the smartest guy in the world. I'm certainly far from the funniest guy in the world. But is there any dimension? There's no math trick here. Does 7 equal 8? Are 7 and 8 the same number? Absolutely not. So I'm going to write the very formal scientific term, rut-row. Rut-row, 7 certainly doesn't equal 8. So we've reached a contradiction. We've reached a statement that is clearly false. Clearly false. And notice, through no fault of our own, x went away. That's just how the nature of the equation was. It didn't look like it was going to do that from the get-go. But once we really dived into the problem, x disappeared. So here's the skinny. Because we eradicated x through no fault of our own, it wasn't our fault that this was a wild equation that wasn't going to work, through no fault of our own, and reached a conclusion that is clearly false. This means no values, yeah, that's fine, of x in the original equation could have fixed this problem. Remember, the whole point of equation solving is to find a value or values of your variable to try and make a true statement out of this. But that's not going to happen. X ended up having no effect on the equation because it actually gets eradicated from it. Thus, are there any solutions here? No. Thus, there are no solutions because there are no x values that fix this problem. That's it. You do the math correctly, you eradicate x, you end up with a false statement, something that's clearly ridiculous. What could you do? You did everything right, and it just fell wrong, just fell weird. It's like being dealt a straight flush in poker, which is an amazing hand. You're going to win that hand 99,999 times out of however many, almost, you're going to win that a lot. But the guy next to you got a royal flush. You didn't do anything wrong. You bet correctly, probably. You knew you had a great hand, so you stay in the pot. You stay in till the very end, and the guy just beats you. He just has a better hand. You didn't do anything wrong. That's just how it works sometimes, and that's how it worked in this case. So that's what's called a contradiction, and it's because we reached a clearly false statement. What if we reach a clearly true statement, but one that still eradicates x completely? That's going to be called an identity. So let's see how an identity is going to work. It is equally as interesting. It will be deceptively similar to what we just did. Let's see if I did my math right here. I didn't. I'm glad I double checked. So we've got 4x plus 12 on the left equals 2x plus 8 minus 3x plus 4 plus 5x. What should I do? What should I do? Exactly. The left-hand side is pretty much fine for the moment. The left-hand side, there's not really anything we can do just yet. The right-hand side, I've got 2x minus 3x plus 5x. We could use the commutative property and rearrange the terms so that they're next to each other. So we haven't combined like terms yet. We just changed around the terms so that they'd be lined up with each other. They'd be all together. And now 2x minus 3x will give you what? Negative 1x. But then you add 5x, what will you get? 4x. Very good. Then you have 8 plus 4. What's that going to give you on the right? Whoa. Trippy, man. Yeah, exactly. Eventually, if you balance the equation out, you're going to end up with 0 on the left, 0 on the right. Now, let's go one extra step and attempt to reconcile our x's, get them all together. But that eradicates the x. Nothing left on the left side. No x's left on the right side. Now, it is a true statement, yeah. 12 equals 12, ba with the ba. 46 equals 46. Is it interesting to say that 12 equals 12? It's not really all that interesting. Yeah, 12 equals 12. My name is Josh. None of that is going to be anything that really jumps out at you today. Some things that would jump out at you. You learned you won the mega jackpot lottery and you're a millionaire or even a billionaire. I think that would give you some exciting news, wouldn't it? Yeah, sure. But 12 equals 12 is far from exciting. So we could move the 12 over and then end up with 0 equals 0, but we've already seen the point. The point here is the x is gone, and instead of reaching a false statement, we've reached or I should say, an arbitrarily true statement. It's true, but it's pretty arbitrary. It doesn't really do anything for us, doesn't flip your boat. Let's translate this. Translation. No value of x that we plug in to the original equation will have any effect on the fact that the equation will always be true. No matter what value of x you plug in, you are never going to screw up, if you will, the truth value of this equation. It's still going to be true no matter what, and x can't possibly influence that. So instead of there being no solution, now x can be any number it wants. You can plug in any value of x that your heart desires. You can plug in 300 trillion, and you're still going to end up with a true statement. You're still going to end up with an equation that's correct, that's true. So x can be any number at once. So the solution set is all real numbers. That's what we're going to say. Now, instead of having no possible solutions, there's infinitely many possible solutions. It turns on a dime just like that. And we'll use the real number symbol, usually, to represent that. So that's going to be called an identity. An identity because both sides are identical. They've met themselves. It's just saying 12 equals 12 is an identity statement, a statement concerning what it is. But it's not particularly interesting in the sense that we didn't really find anything. If you solve an equation and it ends up with this, that means there's something funky going on. The real world application of your equation probably doesn't exist or you set something up incorrectly, it doesn't really tell you a whole lot in most cases, except that there's something wrong usually. So you might think having an infinite number of solutions is a good thing. It's actually not, because that's too much. That doesn't help me to say, I'm thinking of a number between 1 and infinity. Okay, have fun with that. You have too many choices. Okay, let me queue up our next discussion. Give me one moment. What I want to do now, we have a homework assignment over proportions, and we touched on proportions yesterday. We touched on setting up a proportion equation. But all I want to do is I just actually, in a rare move, I just want to work some proportion problems from your homework. That's just how I think the best way to approach this is. You're going to have the same basic problems you'll see, but the numbers are going to be probably different for you. There's a chance it could be the same. You just get a little lucky. So let's take a gander at some of these. An alligator's tail length is proportional to its body length. So what that means is the longer the alligator's body, the longer the alligator's tail is going to be. Makes sense? All growing alligators, they need protein. And when I was a growing boy, I ate SpaghettiOs. How many of you like SpaghettiOs? Yeah, that's good. How many of you, and don't judge me if you don't do this, how many of you eat them out of the can? Yeah, all right, that's not bad. How many of you dump them into a bowl and microwave that? Sometimes, it depends on your mood. Sometimes you're not in the mood. My girlfriend, to this day, because I ate SpaghettiOs so much as a kid, my girlfriend has to suffer me eating SpaghettiOs out of a can, sometimes in front of her. She calls me a monster. She says I'm evil and I need to put it in a bowl and microwave it. And you know what I say to her? I say, I go my own way on these kinds of things. I'm my own man, driving out on my own path. And if you ask me to do it again, if you ask me to microwave it one more time, I probably will. Because I don't want to start a fight or anything. If this is going to cause a fight, it's not worth starting a fight. That's what I say. That's my tough guy voice. So, boom. Anyways, just a little interesting peer into my life. You probably don't care, and that's okay. So, an alligator's tail length is proportional to its body length. An alligator with a body length of 5.1 feet has a tail length of 5.7 feet. That piece of information is going to be kind of like our codex. It's going to be the thing that helps us decode this problem. What is the tail length of an alligator whose body length is 9.5 feet? So we're going to do the top part of our fraction is going to be tail length. The bottom part of our fraction is going to be body length. Why? Well, it kind of, for one, where they put the X here, where they put the X, if X is supposed to be, it's asking for the tail length of an alligator, X is going to be the unknown value. So X is kind of forced to be the tail length. And since X is on top of a fraction, that means the top of the fraction is going to be tail length. The bottom of the fraction is going to be body length. So this piece of information, our decoding piece, the tail length of 5.7 actually has to go on top of the fraction with only one decimal point, not two. And there's no great way to zoom in on this. I'll try. MyLabs Plus is a little finicky when you do that, but I think that's a little better maybe, hopefully. Good. So 5.7 to 5.1. So on average, the tail is actually a little bit longer than the body. That's kind of interesting. And then the alligator of interest has a body length of 9.5. And so it's going to be this ratio, X to 9.5 equals 57 to 51. There's a couple things we can do with this one. So X over 9.5 equals 5.7. Let's solve it. Let's solve it. Now here's the skinny, my friend. We've got decimal numbers. All our numbers here go out to 1 decimal point. We can deal with that. We haven't technically talked about decimal number division, addition, multiplication just yet. So here's a stupid little trick. How many of you want to see a stupid little trick? Stupid little trick wins the bet. I can multiply in order to get rid of decimal numbers. I can multiply the right-hand fraction by 10 over 10. Technically, I can do that without even doing it to the left side because 10 over 10 is just 1. But I'm also going to do it to the left-hand side for a very good reason. That reason is that by doing this, I'm going to basically be moving the decimal point 1 place to the right in each case. I'm still going to have 10x here, though. I can't avoid that, but I'm going to get, this is kind of what we call clearing out decimals. So you're going to have 10x over 95 equals 57 over 51. Now, this may not inspire a lot of confidence, but it is something that we can solve. You are tasked with doing this without a calculator. So we're going to initially attempt it without a calculator. If for some reason the numbers get hairy, we may have to revamp our strategy. But what I can say is that any of the problems you encounter on the exam tomorrow will not require a calculator. The numbers will simply be simpler. In the homework, they kind of throw a little bit tougher, nastier numbers at you because they know you're in a place where you have resources available, you have more time. On an exam, the numbers are just going to have to be a little bit less nasty. So there's a couple things we can do here to simplify our lives. 57 and 51, it turns out, are both divisible by 3. In other words, we can reduce this fraction. I can divide a 3 out of this top, and I can divide a 3 out of the bottom. Groovy. If you divide 3 into 57, you'll get 19, and a better 9 needs to be. If you divide 3 into 51, you'll get 17. So we can reduce this fraction to 19 over 17. And that might help a little bit. That might help us out a little bit. But we still have a few things we have to do. We want to get x by itself. It's being divided by 95 at the moment, which isn't a whole lot of fun. We need to multiply both sides by 95. I'm going to delete this. Mm. 17. We're going to get rid of this 95. We're going to multiply both sides by it. You're going to end up with 10x equals the 19. We're going to multiply it by 95. So as you can see, the numbers are going to get a little nasty. So we have a little manual labor we need to do. 9 times 9 is 81, plus 4 is 85. $1,805 divided by 17. which again may not be anything inspiring. It may not be anything magical, but that's okay. Sometimes you can't avoid it. The last thing we'll do, we'll divide or we'll multiply both sides by 1/10 so that we can get x completely all by itself. You're going to end up with x equals 1805 divided by 170. And we're going to go ahead and leave it in fractional form. If it wants you for some reason to get a decimal approximation, on this one, I would be okay with you using a calculator. Just keep in mind on the exam, you can't use a calculator, but, excuse me, the numbers aren't going to quite look like this. They're going to be a little bit more manageable. So 1805 over 170. 1805 divided by 170 is about 10.6. And so that's how long the alligator's tail length would be if its body length is 9.5. Let's try out another one. Let's see if we can find a nasty one. And so, yeah, you'll see there's just going to be a few problems here that we just have to use calculators. This one won't be one of them, thankfully. This one will be a lot simpler. So here we want to solve this proportion equation. -6 is to 5 as p is to 30, where p is going to be the value that we're solving for. It's going to be what we're trying to find. So -6/5 equals p over 30. They use a p instead of an x here. That's okay. What should we do here? What should we do? We got to get p by itself. What is bothering p at the moment? What is the only action that's happening on p right now? It's being divided by 30. So how can I get rid of that? Exactly. Multiply both sides by 30. Do it to both sides. Those 30s will kill each other, which is what we wanted. And then over here, we're multiplying by 30. That's really the fraction 30 over 1. So we multiply the numerators. We know it's going to end up still being negative. And then 30 times 6, you can do this old school. It's going to be 180. So it's going to be -180 over 5 equals p.
Why would you not multiply p by 30?
Well, what you're doing, okay, so if you're multiplying p by 30, let's say that's the route you wanted to go with it, you would end up having 30p, right? But what are those 30s going to do to each other? They're going to cancel out anyways. So it's the same, it's just 6 of one, half dozen of another, if you will. By multiplying by 30, I'm going just straight to the denominator and killing it, which is what it would have happened anyways. Good question. So now we've got p equals -180 over 5. Well, 180 ends in a 0, so it's divisible by 5. So I'm going to end up with p equals, I'm going to write it on the left now. It's going to be a negative number. And then I just got to do 180 divided by 5, which will end up being 36. 5 doesn't go into 1. It goes into 18 3 times. Bring down the 0. And 5 goes into 36 times. So we're going to end up with -36. as our final answer. Okay, so here's what I want to do now. I don't want to, we're done with that section completely, section 6.2. We're already past what your exam is going to cover tomorrow. So I'd like to not really get into super much more depth about new material. We can get back to that on Monday. What I'd like to do the rest of class is field any questions from you may have about the exam. And I mean specifically content questions. Basically, this can be a review session for the next however many minutes we have left. So you can ask general questions about the exam, but content questions, you can throw one at me. If you're in the Zoomosphere, you can type out a question here. I'll answer it. So what do y'all got for me? Yes. Okay. Great question. It's just convenience. You can, because 30 over 1 and 30 are the exact same number. So either way you want to express it, you can express it how it's most convenient for you. By expressing it on the right-hand side, that just helped me recognize that I was just multiplying two fractions. On the right-hand, that was on the left-hand side, excuse me. On the right-hand side, we can do that. Those 30s will cross out through cross multiplication, and then you would just be left with P over 1. But P over 1 is still just P. So good question. It's basically just convenience. It's how you're feeling at that particular moment and how you want to express the numbers. It's just like I could call 5 15 over 3 if I was so enchanted to do so. And there might be a reason to write it like that, especially if you're adding a 5 plus a 7 over 3. Then if you write 5 as 15 over 3, you got common denominators. So there are times, but it's basically just how you want to express the number for convenience. Good question. Good question. And I'm checking the chat box here in Zoom. What else do you guys got? So they can be general theory questions. Sure. Sure, absolutely. So we want to go over properties of real numbers. It's automatically going to be about real numbers at this point, so I won't write of real numbers. It's implied. The commutative property. There's two of them. There's a commutative property for addition, and a commutative property for multiplication. And it's fairly common sense in the sense that if I add two numbers, it doesn't matter what order I add them in. In other words, A plus B equals B plus A. Where A and B are real numbers. I can also multiply them in a different order. A times B, or just AB, equals B times A. Here, look, it spells ABBA. In other words, for either addition or multiplication of real numbers, you can change the order of the numbers and it's all good. It's all the same. 2 times 3 is equal to 3 times 2. Negative 457 plus 38 is equal to 38 plus negative 457. And be careful with negative signs. The negative must stay attached to the number, and you still have to be talking about addition if you want to flip them. So keep that in mind. So the commutative property is very important. Would you say there's a commutative property for subtraction? Not quite. So for instance, for subtraction, I mean 5 minus 2 is not the same as 2 minus 5. That's not going to be the case because 5 minus 2 is positive 3, 2 minus 5 is negative 3. So there's no commutative property for subtraction per se. However, if you rewrite subtraction as just addition and then slap a negative sign on what was being subtracted or switch its sign, then you can flip them around the addition sign you just created. But we don't have to get too cute with that. So there's no commutative property for subtraction. It doesn't make sense. Is there a commutative property for division? Definitely not. Definitely not. In the case of division, if you have, just to keep the numbers simple, 10 divided by 2, that's nowhere close to the same as 2 divided by 10. Now, what's interesting is you're creating the reciprocal, but they're not the same number. 10 divided by 2 is 5 over here. 2 divided by 10 is 1/5. They're not the same number. But there is a link between them, just not equality. So there's the commutative property. The associative property is not super duper interesting for our purposes. I'll give you a second to finish writing down the commutative property. The commutative property is interesting. There's a few reasons why it's interesting. Again, we won't quite run into them just yet, but it is a very popular property to talk about. The associative property, I'm just going to state it, and then it's really not all that interesting for our purposes. Parentheses tell us when to do what. So what the associative property basically tells us is that ultimately if I have A plus B plus C, if I choose to do the A plus B part first and group those together, then add C, it will result in the same thing as if I said the B plus C part first, because it's in parentheses, then I tack the A onto it after that. It's the exact same thing either way, though. That's actually a justification for certain things in order of operations. That's one of the things that helps justify some of our order of operations things. And what's interesting is that order of operations is not only important for figuring out problems with numbers in them, order of operations dictates why we solve equations the way we do, why 3x and 5x are like terms. It's because we don't know the value of x, so we don't actually know what 3 times x is. We don't know what 5 times x is. But we know that if we were to add them together, you'd end up with the same result of 8 times whatever x is because of order of operations. So it just kind of creates a little bit of an interesting point that we can look at. See, the associative property may not be super interesting, but the distributive property is mega interesting. We call it the distributive property, and they like to tack this on to help you remember it, of multiplication over addition, or even subtraction if you wanted. And this one is a little bit more nuanced. We did a problem earlier today at the beginning of class using it. We had to use the distributive property. And it says if I multiply a number to a product, if I multiply a number to a sum, where I'm adding on the inside of these parentheses, it tells me that I can distribute this A value like that. And do this, A times B plus A times C. The A goes to both of them individually. The distributive property is pretty interesting because it looks like we can't do it because of order of operations. Order of operations says you got to do what's in the parentheses here first, then you can multiply. And what we're saying is, well, we can cheat a little bit, but we still end up with the same thing. I wouldn't call it an exception to order of operations. In fact, it can be proven with order of operations, but it's not something that's immediately obvious just from the way it looks. And then it's important to note the same thing is true for subtraction. You still multiply the A to the B, but then you do minus the A times the C. So you just match up the sign. Where it's really confusing is that if A is a negative number, it's going to negate these values, so it might turn it into subtraction. You just have to know when to do what. We'll give you a second to write that down, and then we'll look at a couple examples of distributive property because it does show up a lot. Well, we kind of did this one yesterday. I'll do a similar one. Say you need to do 6 times, oh, I don't know, 93. Now, in your head, you might just say, well, 93 is about 90, and I can figure out 6 times 90 pretty quickly. But if you want the exact answer, you can turn this into distributive property. You can say that 93 is really 90 plus 3, and it's got to go in parentheses so that I know the 90 and the 3 are linked together and then getting multiplied by the 6. And now what that lets me do, I can distribute the 6 like this. Then I can just do each one individually. 6 times 90 plus 6 times 3. Now 6 times 9 is 54. So 6 times 90 is 540. You just multiply it by 10. 6 times 3 is 18. So we end up with 558. How many of you want to see something real cool? Want to see something real cool? I like the way you think. If I were, let's say, I didn't want to use this cutesy little, oh, turn 93 into 90 plus 3 and distribute. I didn't want to use this cute little trick. In other words, I was just going to do my old school multiplication. Well, you're actually doing the exact same thing. You're doing 6 times 3 first, you're doing 18, and then you carry the 1. Then you're actually doing 6 times 90. You may not think it, but you are, because this 9 is not just supposed to be a 9 by itself. This 9 is representing a 90. So I'm doing 6 times 90, and then I add the 1 just like I would have added the 1 from this 18 over here. And I still end up, 6 times 9 is 54, plus 1 is 55. So doing old school multiplication is actually just the exact same thing as distributive property. And so that's cool to know. If you don't believe me, we can look at it another way. While I could put the 93 first, I could put the 6 on top, and I could multiply it this way. In doing so, I would take this 3 first. It would be 3 times 6, which is 18. Then remember, you spot yourself a 0, don't you? And you come over here to this 9. And you would do 9 times 6, which is 54. Wait a minute, that's just the 540 plus the 18 we did the other way. And yeah, you still end up with 558 if you write it that way. So it's pretty neat how we do kind of the old school multiplication by hand, really is just us doing it via distributive property. We didn't know that until now. We'll do one more example with the distributive property, and we'll bring a variable into it. No, let's make it more interesting. $14, and then in parentheses, 3 minus 2x. All right there, Pilgrim. You're going to do 14 times 3 first. Then you do 14 times 2x. There's a minus in the middle. $14 times 3, well, that's not on our 12 by 12 table. So if we want to do it old school, that's fine. 2 times 4 is 12, carry the 1. 3 times 1 is 3, plus 1 is 4. So we're gonna end up with 42 minus. Now, this is the number 14. It's not 1 times 4. It's the number 14 times 2. And then secretly, it's also times x again. Because when you write 2x, you're really saying 2 times x. Now, I didn't know what 2 times x was up here because I don't know the value of x. So do I know what it is down here any more than I did before? In other words, we're just going to end up having to write x because I don't know what x is. It's just going to be something that gets multiplied. But can I figure out what 14 times 2 is? It is, yeah, it's going to be 28. Bet your bottom dollar you can do that. And then here you go. That's all we can do with this problem. We were just distributing it, expanding it, in other words. That's all we can really do with it. If we were writing equations and trying to solve it, we might have needed to distribute to get the ball rolling, like that very first example we worked in class today. So the distributive property is very interesting. It also, if I started with 42 minus 28x, it turns out I can factor a 14 out of it. And by doing that, I would just end up with what I started here. So it just depends on what you're being tasked with. We'll talk about factoring later. You don't have to know about it just yet, but that's all factoring is. Factoring is basically going the reverse process of the distributive property. And in fact, that's exactly what it is. Because the two sides are equal, you can go either direction. So that's cool. Any other questions? More questions? Nothing in the Zoomosphere? Anyone else? Anything you want me to touch on? If not, we'll call it. And that's cool with me. It's just up to y'all. Going once, going twice. Sold. Don't go just yet. Let me take attendance. And what I'd like to do is we'll have our exams mostly on Thursdays. Every Wednesday that before an exam, we're going to spend some time lecturing, and as long as we don't lose track of the schedule, or as long as we don't get behind, in other words, I would like to spend time reviewing like this. I think it's helpful right before an exam. So you can generally come in on the day before an exam with some questions you may have. And I'd like to devote roughly the second half of that class to it. I can't promise it'll happen every time though. Simply, especially if we get behind, and that just happens.